Welcome back to our lecture series on Material Science and Metallurgy subject. Myself, Dr. Bhanu Prakash, working as an Associate Professor in the Department of Mechanical Engineering at MLR Institute of Technology. Today we will discuss about copper alloys, in particular that is bronze. In the previous lecture we have seen copper alloy, that is brass. We have discussed different varieties of brass, its manufacturing process, properties, and its typical applications, and certain limitations also we have discussed. In today's lecture also, we will talk about the bronze material particularly. So what is the definition of bronze? So what do you mean by that? The basic composition and its classification, and we discuss about the microstructure, what we can observe in the bronze microstructure. Then we look at certain manufacturing process that have been adopted here. Then we will discuss the properties of bronze, certain advantages and limitations, applications, and comparison with the brass. We'll talk about it, and finally we'll summarize and discuss the key takeaways from the lecture. So bronze, what is a bronze? Bronze is primarily a copper alloy where the principal metal is copper and the alloying element is a tin. So the primary alloying element in the bronze is a tin, so which is typically ranging between 5 to 20%. It is almost half what in the brass zinc composition. So in the brass zinc composition, we have, if you recall, we have discussed it is between 35-37% and above that as well. And here tin is added at a range of 5 to 20%. In addition to the tin, there could be other variants as well, other alloying elements as well, which in turn bringing the new variety for the bronze, if it is been added with aluminum or silicon or lead. We will see the classification of the bronze and we will discuss about it. In some certain special alloys also we talk about it. If you see the historical significance, bronze is which is the alloy which has been used from very olden days, right from 1300 1200 BCE. From that era onwards, this material has been used, and we call that particular period is Bronze Age, where most of the metals are being replaced with the bronze, and the use of bronze is extensive in all the empires, the kingdoms. It is the first alloy that has been used for tooling or in the weapons as well. So we have this Stone Age, Bronze Age, then we talk about the Iron Age, and currently the latest advanced materials, and Silicon Age we call it, or Nanomaterials Age we can call it. The key features of the bronze material, so it has very high strength compared to the brass. So relative to the brass, it has very high strength, and it also offers excellent corrosion resistance, and it is having low friction coefficient as well. So these are the primary key features which makes the bronze its extensive use in almost every engineering segment during this period. In the Bronze Age, all the tools, weapons, and certain statue or architecture purpose as well, people have been using the bronze material extensively in the kitchenware as well. So if we talk about this, why did bronze replace the pure copper for swords in ancient times? So what could be the reason why? So we know that pure copper is weak and soft in nature. So they don't have that great properties, the great mechanical strength. Uh, it is not having that good property, and it is soft in nature. And so it cannot be applied to the tooling applications, tooling or weaponry applications. And whereas the bronze, when it is mixed with the tin, it is giving very good strength, and that is the one of the reasons and that is a major reason why bronze has been used. Bronze has been has become the replacement for copper, pure copper, for the swords in the ancient times. If you look at the classification of the bronze, so we have tin bronzes, that is a classic bronze, where you can see the copper that is mixed with the tin. So 5% of the tin can be observed, and in addition to that, we are also having certain amounts of phosphorus. Phosphorus is restricted to 0.1 weight percentage of the phosphorus. So this is the classical bronze, which is tin bronze, and its grade is C51000. Then we have aluminum variety, aluminum variant, aluminum bronzes, so which is given with the grade of C95400, where aluminum is being added significantly, that is 11%. It is significant addition, 11% of aluminum can be observed, and in addition to that, 4% of iron also has been present in aluminum bronzes. Then we have silicon bronzes. So silicon is added up to 3% here. So with a grade of which is given grade name of 65,500. So C is a copper here. So leaded brass, another variant. So leaded brass, which is having 7% of tin and 7% of lead here, which is given the grade name as C 93,200. So these are the four varieties that we can have in the bronzes. First one is the tin bronze, that is a classic bronze, which is having majority of the alloying element is the tin. Then we have aluminum bronzes, up to 11% of aluminum can be present here. Then we have the silicon bronze, 3% of silicon is being added here. Then we have leaded bronzes, so where 7% of lead and tin is also present of 7%. So equal amount of tin and lead can be observed here. So if you look at the properties of these different class of materials, starting with the phosphorus bronze, where tin and small amount of phosphorus can be present. This is also called as your classic tin bronzes, where a small portion of phosphorus can be observed here, right? So which is similar exactly. So 51,000, C51,000, what we are talking about. So this variety of bronze is offering excellent fatigue resistance. So under the cyclic loading, it performs very good. Then we have aluminum bronzes, where you can see aluminum as well as the iron present in the material, and remaining is a copper, which is having excellent wear resistance. So the hardness of aluminum and the iron, which is contributing and to the copper significantly, and we can notice extreme wear resistance can be observed with the copper. Obviously it cannot be compared with other elements. So in the copper alloys, aluminum bronze, with the addition of copper that has been added with aluminum and iron, which is found to be having extreme wear resistance. Then we have the silicon bronze, where copper and silicon has been present. So copper is 93% and remaining is the silicon. Silicon is up to 3%, which is basically bringing the weldability. So weldability of the copper alloy is very good with the addition of silicon. So it is having excellent weldability characteristics. Then leaded bronzes, where we can see 7% of tin and 7% of lead. In addition to that, we can see 3% of zinc also, and the remaining is a copper. So which is offering lead is present at the grain boundaries, and so it is offering extreme or the good superior missionability. Otherwise, copper, because of gumminess or stickiness, its missionability is little challenging for us. But with the addition of lead, where the lead is segregating or sedimenting at the grain boundaries, is offering very good missionability to the copper alloys. So here phosphorus deoxidizes the tin bronzes. The small amount of phosphorus deoxidizes the tin bronzes, and that's how it is reducing the porosities that might be found in the castings. So the chance of porosity can be reduced with the addition of phosphorus, and that is very small quantity we are adding with 0.1% of phosphorus, which reduces the porosity in the castings. If you look at the microstructure, tin bronzes are having alpha phase, which is copper rich phase. Then you have delta phase, where we can see the intermetallic compounds. Copper and tin intermetallic compounds can be observed in the delta phase, which is found, but which is hard, but it is brittle in nature, tin bronzes. Then we have aluminum bronze. So aluminum bronzes are also having alpha phase. Then we have the beta phase, and in addition to that, we can able to see the K phases also. These are basically iron and aluminum intermetallic compounds. So iron and aluminum intermetallic compounds present as K phase, so which is basically offering excellent wear resistance characteristics. The delta phase that is present in the tin bronzes basically increases the hardness but reduces the ductility, and overall the brittleness of the material is getting increased. So this can be optimized with the heat treatment process. A heat treatment process can optimize the balance. Okay. If you see the mechanical properties of all these alloys, wrought alloy and cast alloys, and this is a phosphorus bronze or the tin bronze, we can say. This is we have aluminum, then we have silicon, then we have here is our leaded bronze. So if we see, right, so if you see its tensile property, so our aluminum and iron, the presence of iron, so its tensile strength is also shooting up significantly, which is 750 MPa. It's a good number. In general, we have, just with the addition of tin alone, it can have tensile strength up to 600, decent, very good, pretty good number, tensile strength. And if you look at the elongation or the ductility of the material, so silicon is giving very good ductility. And if you see the hardness parameters, so hardness is, because of the phosphorus here, it is becoming very hard, our wrought phosphorus bronzes, because of the presence of the delta phase, it is becoming very hard and brittle, and so its ductility is significantly reduced. Now if you see the hardness value, so hardness is very good for aluminum and aluminum based bronzes. With the addition of iron, it is getting good tensile strength as well as the hardness. So there is a trade-off which we can work with. That is like the amount of tin and the aluminum percentage. If it is increasing in the copper, it is increasing the strength, but basically it is decreasing the ductility. So you can observe it here also. 11% of aluminum, it is significantly reduced, which can result in very good, very low ductility. So elongation is pretty low, except for silicon bronzes. In the silicon bronze, we don't have the presence of tin here, or very limited amount of tin is present. And with the addition of silicon into the bronzes, we have pretty good ductility here. And if you see the corrosion and wear resistance properties, particularly if you see with the sea-water resistance, aluminum bronzes outperforms stainless steel in marine environments. So stainless steel, even though it is being told as very good, it is having excellent corrosion resistance among the steels, but that cannot match with aluminum bronzes. So always aluminum bronzes outperforms the stainless steels, especially in the seawater applications, seawater corrosion resistance applications, marine environments. In the case of oxidation resistance, aluminum bronzes, copper itself, bronze can have an layer, oxidative layer, and which is in general is acting like a corrosion resistance layer. And with the addition of aluminum into the bronzes, aluminum is creating this protective layer, Al2O3 ceramic layer, and that is protecting that is offering, in turn, it is offering the corrosion resistance of the material. If you see the VR applications, K phase in the alpha bronzes resist the abrasion. So K phase, that is a intermetallic compound. What is this intermetallic? Aluminum, iron, intermetallic compounds. This is intermetallic compounds basically, and these intermetallic compounds in the aluminum process which resist the abrasion, and these are the ideal candidates for bushing applications. If you see the marine application, if you see the applications of bronzes, it find its applications in the marine, electrical, art, and automotive, and some of them are listed here, and there are many applications that we can notice from the BCE era bronzes. So particularly if I take the marine applications, aluminum bronzes are very good. They find its extensive use because of their very high seawater resistance, that is a corrosion resistance, and that's why marine propellers are being manufactured using this variety, and pump casings also manufactured using this, submarine pump casings also manufactured using this aluminum bronzes. Then we have electrical applications. For electrical applications, general classic bronze can be used, where certain springs and connectors have been manufactured using bronze. Then art and architecture purposes, we have this silica variety, where it is having very good ductility. So for art and architecture purposes, it need to have very good ductility. So silicon bronzes have been ideal candidates for making sculptures, certain sculptures, and roofing. Then in the automotive segment, we have this variety, leaded, because machinability is that's one of the prime requirement. So leaded bronzes are being used for manufacturing certain bushings and bearings. So the famous Statue of Liberty that we can see, its skeleton is made out of silicon bronze. Why silicon bronze? Because of its good ductility. So you can mold it into your desired shape if you have very good ductility. Your Statue of Liberty skeleton has been made out of silicon bronzes. If you see what are the manufacturing processes that have been adopted for bronzes, so primarily casting we do, particularly the sand casting can be performed for manufacturing the large propellers, marine propellers especially, that is aluminum bronzes. Then for the forging is another manufacturing method that you can use for hot forging for aluminum bronzes, where beta phase, it offers the beta phase workability is possible. So because of that, hot forging is possible for aluminum bronzes. Then for machining operations, basically leaded brosses are suitable. So leaded brosses are suitable or preferred for screw machining. So these are some of the manufacturing process that we use: sand casting, then you see the forging, hot forging. Then for machining, leaded bronzes are being used. It is not bronzes; it is basically bronzes, basically leaded bronze. Sorry for that. Then advantages: it is having good strength when compared to the brass. It is having outstanding corrosion and erosion resistance or abrasion resistance, particularly with seawater corrosion resistance or oxidative corrosion resistance. Both are very good. Then biofouling resistance is also very good. So if any biological materials getting adhered to the metals and causing certain reactions, so that can be avoided using these these bronzes having excellent resistance against biofouling also. Then there are certain limitations which we can talk about. So these limitations are high cost when compared to the brass because of the addition of tin and aluminum. That is little slightly manufacturing process slightly challenging and material cost. So relatively it is higher cost than the brasses, and it involves a complex heat treatment process for certain grades of bronzes. So these are limitations or challenges involved with bronzes. Apart from that, bronze has been extensively used since ancient times. And we have certain special bronze alloys that we can talk about. So that is, one is beryllium copper and the beryllium. So beryllium added to the copper alloy. It's a special bronze alloy. It's not technically a bronze, but it's worth mentioning. So where we will be adding 2% of beryllium, and it is given the grading as C17200, which is basically highest. It is offering highest strength copper alloy. So among all copper alloys, this beryllium copper will offer excellent strength, which find its applications in manufacturing the springs, aerospace and other applications, aerospace components, certain aerospace components. Then we have nickel aluminum bronze, where we'll be adding nickel, and aluminum is also present here. Aluminum, in the aluminum bronzes, I would say nickel is being added. So this finds its applications in the marine conditions. Aluminum bronzes are, in fact, in turn, they are suitable for marine applications, and where if you have extreme marine conditions like very high, very low pressures like submarine applications, these nickel aluminum bronzes are being suitable. So these are the two special bronze alloys which are worth mentioning. So if you look at the comparison with the brasses, bronze is having a higher strength, almost double the strength, tensile strength, 600 MPa. Then corrosion resistance is excellent for the bronzes, and that's why it finds its applications in the marine or seawater applications. And whereas brasses are often found with dezincification risks that we have discussed in the previous lecture. And but the condition is here in terms of the cost or economy. Bronze is relatively higher cost when compared to the brasses, where brasses are being alloyed with the zinc, and this is alloyed with bronze is alloyed with the tin or aluminum. So overall, we can make this quote: if you are looking for machinability and the overall cost of the material to be relatively low, then our option could be the brass. If you are looking at performance, particularly in harsh environments like seawater or marine conditions, we can opt for bronze. So this is the trade-off that we have to make here with the materials. So if you summarize, tin bronzes, the classic bronzes, they dominate in high fatigue applications, which basically it offers excellent fatigue resistance. So the springs and bearings are being for springs and bearing applications. These tin bronzes are being employed. Then aluminum bronzes are they excel in the marine or seawater or wear environments where it offers excellent wear resistance as well as seawater resistance. Then we have silicon bronzes which offers unmatched weldability for the structural art. So they offer very good weldability, and also in addition to that, it is also having very good ductility. Its ductility is also pretty good. Percentage of elongation is also pretty good, and that makes good moldability also, which makes it suitable for arc or architecture applications. So bronze is which is an alloy that built empires once in the ancient era. Now it is excelling in today's world. It is excelling in propeller ships, particularly in submarines, and in the electronic components which connects the circuits. So for our lecture content, these references are being useful for making these slide content. So here is your question for pondering your brains. So why is aluminum bronze used for submarine components instead of stainless steel? Already we have discussed about it. So here is your hint also, which is galvanic compatibility is a hint to you. So um, go through or ponder upon this question, and you can give your responses in the chat in the below. So that's all for today. So we will discuss another variety of copper alloy, that is cupronicals, in our next lecture. Thank you.